This is not. All right, I still want your sheets for this. I decided to try something a little bit different. I read this article the other day about math and how there's different styles of teaching math. One style is you don't tell the kids anything, and then you have them try to figure out the problem. Basically, this is an elementary school, by the way. And the kids actually can figure out, how to solve a certain fraction of the kids can figure it out, and then they tell the other kids, and then they end up figuring out how to do it. Because, is this in the book? This is not in the book at all. And so I have every semester I have a pretty, larger proportion than I like of students who say this is not in the book. I can't learn this if it's not in the book, right? But it's such an easy process that trying to convince them, yes, it's not in the book, but it's straightforward. It's just a simple step-by-step thing, just like the acids and bases. And there should be no reason to put this kind of mental block, which is, I think it's 100% psychological block that they put on themselves. And when it comes to the exam, it's blank. And so I've been thinking, how to reach out, because if I just repeat it, I don't know, it's not that effective. So, there's a lot of stuff you can learn on your own, and you might be limiting yourself dramatically by not giving it that effort. And so let's take a look at this particular problem. I said that there is a redox reaction, but let's confirm that. Maybe you found something else, right? And so let's take a look at how we would approach this. Actually, I'll just do it here. So looking at the steps for doing this, and I looked at the answers, and some of them were pretty close. Yeah, you can turn them in. You can turn them in later, too. I just wanted to get an assessment. But the first thing, what do? You inventory. And there's nothing difficult about inventory, as long as you know solubility and what? And electrolyte properties. If you know solubility and electrolyte properties, then you can do it. And so what we have is iron 3, chloride, what else? Silver, nitrate, and water. Then what we do is we do the same thing that we did for acids and bases. Rather than looking for the acid and the bases, we're going to be looking for the oxidizers and reducers. So there's a left-hand side of the chart and a right-hand side of the chart. And so we know which side is which because we know for the oxidizers it has what element? Fluorine. And so iron 3, we see this is an oxidizing agent, OA, because it occurs on the left side of the chart, right? Chloride. It's on the right side, and the right side we call reducing agents. Silver ion. Oxidizing. Maybe I should color code these. Make it easier to see. Nitrate. Nitrate is an oxidizing agent. I'm going to put an asterisk there. Water. It's on both sides of the chart. And so that means water is both an oxidizer. It's not amphoteric, but it's analogous, right? And a reducing agent. This, for acids and bases, it's not that difficult to tell what's amphoteric, but for redox agents, tell me another one that occurs as both an oxidizer and a reducer.
Redox?
Yeah, on the redox chart.
Yeah.
Sulfate? No.
Wait.
Look carefully. Sulfate is not on both sides of the chart.
Hydrogen peroxide?
Hmm?
Hydrogen peroxide?
Hydrogen peroxide, yes. Hydrogen peroxide, oddly enough, is both an oxidizer and a reducer. Its oxidizing properties are much stronger than its reducing ability, but it can do both. What else?
Wait, so why is sulfate not analogous?
Oh, maybe I'm thinking of the wrong chart.
Yeah, I think.
So where do you see sulfate on the left? Tell me.
It's the third one. It's the third one. As a reducing agent?
Okay, third one on the right side,
Yeah.
right? Where do you see it on the left side?
It's near it's underneath copper too.
Underneath copper?
Yeah.
Copper 2 ions?
Mm-hmm.
Okay, yeah, there it is. So let me take that back. Sulfate is both oxidizer and reducer. I forgot this one had sulfate as the oxidizer. Our room chart does have sulfate as an oxidizer. It does not have sulfate as a reducer in our room chart. And so this one has both. All right, so sulfate, what else? Do you see any others? Iron 2. Iron 2 is probably the most common. Water and iron 2. Right? And so those ones you should register in your memory once in a while. Sulfate is not that common. The reason why sulfate's not that common is take a look at what of the third one from the top forms. Do you see that? What's the oxidation state of sulfur in S2O8 2-? S2O8 2-. What is the oxidation state of sulfur? All right, so we have 8 oxygens. Each oxygen is 2-, so that's -16. And so we need each sulfur to be +7. That's correct. Is +7 an unusual oxidation state for sulfur? Highly unusual. Why is it highly unusual? Why is it highly unusual?
It's balanced.
Yeah, how many valence electrons does sulfur have? 6. So if it loses 7 electrons, what did it also lose? A core electron. Losing a core electron costs huge amounts of energy. And so this is why a species like this one, which is the S2O8 2-, is a very rare ion. You know, it's an extremely powerful oxidizer. It's extremely powerful because sulfur is missing one of its core electrons. You know, most things, they'll just lose all their valence. Like, for example, carbon dioxide, +4. It's lost all its valence. But would you expect carbon to go +5? No. I mean, because it would have to lose a core electron. Now, sulfur is a lot bigger, so the core is bigger. You know, there are more shells. So there it starts, the possibility of losing a core electron is more probable. Whereas something like carbon, where the core is so small, you know, those electrons are so tightly held, it's highly unlikely. All right, so that's an unusual species. But anyway, iron 2 is not. Iron 2 is very common. Water is very common. And so what do we do next? Yeah, we just find the strongest oxidizer. And the strongest oxidizer should be closest to fluorine or closest to lithium? Closest to fluorine. So which of these is the strongest oxidizer? All right, nitrate is. But it's nitrate with what? Extra ingredient.
More water.
not waters.
Protons.
4H plus. H plus is
Protons.
acid. And so that's a key ingredient. And so do we have acid present? Is there H plus in the inventory? No. And so what this means is like this. Let's say you're trying to bake a cake. You have the flour and you need 4 cups. 1 cup of flour, which is the nitrate, 4 cups of sugar. Or maybe I have it backwards. But anyway, what if you're missing all the sugar? Are you still going to bake the cake?
Nope.
Is it going to come out a cake?
Nope.
No. And so the situation with nitrate is it's missing a key ingredient. We need that ingredient. Why do we need the H plus? Is there a reason why we might need the H plus? Is there some kind of pattern to the H pluses?
Don't they like? Yeah. Well, don't they cancel electrons or?
No, they don't. The oxidation state of H doesn't change. It stays +1 on the left and +1 on the right. It doesn't gain or accept electrons or whatever else. What is the purpose of the H? Did anybody see the pattern in the H plus in the redox chart? Yes. Good memory. Good memory. So I'm glad somebody remembered. All of them form water. If you didn't have H plus, what would you form? Not water. What? What would you form? Not peroxide. Not hydroxide. If you didn't have any H plus, you would form. We talked about this briefly. Okay. Nobody remembers? You'd form oxide. Remember? Oxide. You know, these. Let me tell you that. You know, there's a certain. There are two levels of problems on tests. There's the regurgitation of things you've heard before, like this. Maybe you didn't catch it, and so maybe you didn't hear it. You know, but some people heard it, some people caught it, and there's that. There's the that type of material, and then there's the application where it's something you've never heard before. You know, and so you see this pattern. Maybe you see a similar pattern with other systems. But anyway, we'll go back to that. If we're missing, the reason I have this asterisk here is because we're missing the key ingredient. And we're missing H plus, which is critical to stabilizing the oxide, because when oxide and H plus combine, it forms water. And so that's a very important part, because now we're not forming something stable like water, we're forming something unstable like oxide, so it's not going to behave as powerfully as it normally would. Nitrate is an extremely powerful oxidizer. You know, all chemists are afraid of nitrates, right? Because of things like Texas City and others. You know, you get a reducer in there, and you're going to have a. But if if there's no acid present, it's going to be a lot less reactive. And so, since this is missing an H plus, we're going to eliminate it off our list to consider, because we don't have that H plus present. Yes?
Do you need the 4 H's in there? Or there wasn't
No, you don't need 4 H's. It's just reacts in a 4-to-1 ratio. You could have 0.1 H's, but you know, all it means is you'd have a lot less nitrate consumed. Just a 4-to-1 ratio, no matter what. But you need a decent concentration. Normally, when we're doing these predictions, you know, we assume something. We assume that we have a reasonable concentration of species. And the reasonable concentration, the assumption that I've been making all this time that I haven't told you, is that we're dealing with 1 molar solutions. Now, if we make these concentrations very dilute, then our predictions might not come out right. There's a tiny bit of H plus in water, you know, that gives rise to pH, right? But that tiny bit of H plus is not nearly the concentration required to get this reaction to go as is. You know, so concentrations are important in chemical reactions.
So the reason that we're not using nitrate is because we don't have, you know, water in the...
Right. Are you gonna? Let's say you ran out of flour, but you have lots of sugar and eggs. Are you gonna make pancakes?
Nope.
No, the same thing here. You know, oh, we got the nitrate, but we don't have any H plus. We're still going to make it. You know, is it going to work?
So if it did have H plus, then
If it did have H plus, then we found it. This is going to be the strongest oxidizer. So, for example, if I added HCl as an ingredient, you know, if I did this, if I did FeCl3 plus HCl plus silver nitrate or something like that, or HNO3, then it would work. Or if I just use HNO3, you know, as long as I have some source of H plus, I'm set. Or as long as I have H plus in the inventory, I'm set.
So you're saying you are eliminating the NO3 minus because to be a strongest oxidizing agent, you need H plus, right?
Yes. So the question was, I'm eliminating nitrate because to be an oxidizing agent, we need H plus. In Chem 1B, you'll learn this. In Chem 1A, we're going to eliminate it because we don't have the H plus. The key ingredient, one of the key ingredients is missing. In Chem 1B, what we'll learn is that, you know, the concentration of the H plus will have an impact on the strength of the nitrate. And so if we don't have much H plus present, the strength of the nitrate decreases. We can actually calculate the decrease in the strength depending on how much H plus is present. This H plus, even though it says 4 H pluses, that H plus is 1 molar. That strength, that, you know, it gives you the strength in terms of volts. That strength is based on 1 molar concentrations of all these species. And the ratios, the coefficients, just tell you what they react in, how they react. That's it. And so again, the analogy here is, yeah, if you're missing, let's say you're missing, you have the car, but you don't have any gasoline, you're not going anywhere, you know? And so this is the same thing. Okay, so we eliminated that. That means what is the next strongest oxidizing agent? Silver ion? So silver ion is the next strongest oxidizer. So we're going to go ahead and choose this one as the strongest oxidizer present. Okay, now we only have 2 choices for reducing agent. Chloride or water. Which one is a stronger reducing agent? Water? Water is the strongest. Do you remember, I told you chemistry is a bit of memorization? There's a bit of memorization involved? Well, there's one thing you have to memorize when you're using this table. We predict water, but this is the only one you have to memorize. This is the only exception you must memorize. For the table. And that is water versus chloride. The chart says water should win, right? Water is stronger. And so the chart picks water. But you should know that chloride will be stronger because of another reason. Let me tell you the reason why chloride is stronger.
And this is for reducing agents?
Yes, only for reducing agents. in order to for chloride to lose an electron, there's an electron out here, the outermost electron, right?
Yeah.
And some oxidizer comes in and takes that electron, grabs that electron and takes it. That's what oxidizers do, right? And so if I have a chloride here, the oxidizer just needs to pluck an electron from the outermost shell. However, for water, what has to happen? Well, for water, what is going to get oxidized in water? The hydrogens or the oxygen? Well, the oxygen, because the oxygen is -2 as far as the oxidation state. And so for what has to happen is the oxidizer is going to come in, and it's going to be a lot more difficult because the oxidizer comes in, and what has to happen? They just don't pluck electrons off that oxygen. Do you know what has to happen? The whole thing has to break apart and rearrange such that I end up with O2 gas and 4H pluses and the electrons. And so what has to happen is a whole lot more electron rearrangement needs to occur. And so what this has to do with is something called kinetics. What we're looking at is the thermodynamics of reaction. Have you heard of kinetics and thermodynamics? But kinetics deals with the speed. You know, even though energetically it's more favorable to get this because these are more stable relative to this, kinetically it's more difficult. You know, kinetically this is much more easier because come in, pluck it off. Even though it costs more energy, in the long run, in the short run, it's an easier path to take. What would the analogy here be? The analogy here would be like this. Do you want a long-term investment that gives you a little bit more, just a little bit more money? Or do you want a short-term investment where you get almost the same amount of money, but you just get it right now? What would you rather have? Well, you know, this trade-off in nature is played out like this: the short-term gain, right? Rapidly, versus the long-term here. So this is why we have to pick chloride, even though we should have picked water. Does that make sense? Okay, that's going to be the only exception on this table. Maybe I started off with the most difficult problem here.
Yeah.
All right, so continuing on here then, this is it. What does chloride want to do? Now we pick chloride. This is going to be our reducing agent. And what was it, silver or iron? Silver ion. This is going to be our oxidizing agent. Does that make sense?
Yeah.
All right, then we figure out what they want to do. So chlorides, what they want to do is they want to go to chlorine plus 2 electrons. And then silver ions, they want to gain an electron to form silver solid. So these are the half reactions. Once I get the half reactions, then I have to make sure the electrons cancel out. And so when I look at this, I got two electrons here, so I'll need 2 electrons here so I can cancel those out. And then I'll add them up. And so when I add this up, 2 chlorides plus 2 silvers yields chlorine plus 2 silver solids. All right, then I have to figure out the driving force. So I take a look. Chloride is a reducing agent. Silver ion is an oxidizing agent. Okay, going backwards, what's the oxidizer? What's the reducer?
Chloride.
There's no chloride going backwards. Chlorine is the oxidizer. And we can see it gaining electrons as we go backwards. And silver loses electrons going backwards, so this is our reducing agent. And so we end up with, well, what's
That's a spell.
easier to compare, the oxidizers or the reducers? All right, let's compare the oxidizers. Which one's stronger, chlorine or silver? Chlorine stronger? Silver is weaker? Brian? Yes? Okay, then we look at the reducers. The reducers must follow the same pattern, do they? Yeah?
You should.
Yeah, they should. So silver's got to be a stronger reducer than... Wait a minute, though. We formed a precipitate of silver metal. Formed a precipitate of silver metal. Should we go ahead and... Yeah, no. The answer is no, because this is redox. This is not metathesis. Formation of a precipitate is not a driving force in redox. And so, you know what we get? No driving force, no reaction. Okay, this is no reaction for redox. And this was the most probable redox reaction to occur. Therefore, all the other potential collisions are even less likely.
Wait, why is that again?
What is the formation of PPTs?
Wait, what's the driving force for redox?
Okay, let's go in order.
Well, I just wanted to know. I thought the driving force was like reducing agent and strong reducing agent.
Yeah, the driving force is going from stronger to weaker. We're going
okay, I
from
see.
weaker to stronger,
Yeah.
which is not favorable.
All right.
All right, what's the next question?
So that would be the driving force for redox.
Yeah.
Stronger to
Stronger, less stable, to weaker, more stable. All right, why? Somebody answer this. I said it about 2 or 3 times. Why is formation of a precipitate or gas not a driving force for redox? Huh? The oxidation states are changing, right? In metathesis, the oxidation states don't change. And so if you have sodium ion, it stays sodium ion on the left and it stays sodium ion on the right. But in redox, if you have sodium, it's sodium metal on one side and sodium ion on the other. Are they equally as stable? No, not at all. And so it's the nature of the element, the stability of the element that changes dramatically, much more so than just forming a precipitate. Forming a precipitate, yes, that's more stable, that's good, but when you look at the energy difference between sodium metal and sodium ion, it's huge. Did I show you the disposal of sodium? Yeah. You can see this tremendous amount of energy difference there. So I was wrong. There is no redox reaction here. No redox. There was no reaction at all. But we can figure it out. All right, so what I want you to do is I want you to continue working these, and you're going to have them checked off from me. And then I'm going to interrupt sometime. We'll talk about the report. Oh, we're not going to do the experiment yet. We're going to do the experiments at the end.
Okay, so how, like, what if, say that it was switched around? Like, is there any way you could switch them around by accident and then get a driving force?
These?
Yeah.
No. Switch around and we'll wait.
Like, say that you, like, you put the half reactions, like, a different way.
No, there's only one way to put the half reaction.
How's that? 'Cause, like,
You can't put the half reactions any other way because I'll stop it.
as long